So my name is Erik Nordmark. I work at ZEDEDA, a company headquartered a couple of blocks down here. And I'm going to talk to you a bit about deploying applications at the edge and what are the challenges that people will face, not only about security. This is based on an amalgamation of sort of true stories, things we've heard from people that we've worked with. So hopefully this is enlightening. In many cases, people have built something where they have something out at the edge, right? So I should point up there. I can't jump in front of the screen. They have some sensors out at the edge. They might have some IoT gateway that takes that stuff, comes in over whatever connectors, ships it out to the internet towards the cloud. In the cloud, they deployed some things that can run some analytics, some AI on that. They have some runtime, be it Docker, be it Kubernetes. It could be virtual machines as well, but let's say they're running some set of 5 containers over there to accomplish this work. And this works well, right? It's functional. But then they realize that as they scale this stuff up, they're shipping a lot of bandwidth over there, particularly if they're shipping video. So they say, okay, how do we actually evolve it to this system where we're shipping less data to the cloud? And we can actually, by doing some of this stuff, running some of these containers out locally at the edge. And the other thing they might want to get is that if this is actually reacting to the data, that you can actually do some local decisions out here. That some of these containers actually, some of the applications running here, they actually change something, sound the alarm, whatever type thing. I see somebody doing something without a hard hat at this construction site, what do I actually do, right? So they can get those benefits. So that means they might need a more capable server out there with a GPU. And they'll have some run times to go do that stuff. So that's what they want to accomplish. And the sort of engineer, DevOps, whatever, goes ahead and figures out, okay, I'll grab some hardware, I'll select some hardware, some GPU vendor, whatever. I'll pick my favorite Linux distro, right? And I'll go and deploy this stuff. And they try it out in the lab, and it works just fine. So we're done, right? And then they say, okay, now we're going to do a proof of concept out at the edge. Well, the edge might look like this, right? This is a machine sitting in a factory. Or it might be sitting on some truck, maybe with some satellite communication, whatever, going out to oil wells or something, right? So that's actually might be the deployment target, not their lab. So that's actually a bit different. So what is actually different? Well, people might not think about this, but you start saying that, sure, I've been running this stuff in my lab, and the internet is rapid, or when I run it in the cloud, right? This could have outages, in some cases intentionally, that they don't want to spend money on that satellite for sending useless data, only for critical data. So the applications might not see connectivity to the cloud for hours or days. Or it's just that it drops out occasionally because the truck is in the tunnel or whatever, loses cellular connectivity. So you could have those, right? There could be other partial ones. This is sort of in the advanced part of the course, right? Well, is that, even when that network is working, is it actually fully transparent? I've talked to people that have tried deploying things, and they said, we built this using WebSockets. But WebSockets doesn't go through the enterprise proxies that are sitting in between us, right? So they need to use a different protocol, a mechanism to transport the stuff. So there are various stumbling blocks that people can run into as they go deploy the stuff, just to move a few containers out to the edge. So that's one thing on the connectivity side. The other thing that sort of surprised me the first time I ran into it was, yeah, people have built this stuff using containers running in the data center or in the cloud or in their lab. Those systems run on UPSs, right? There's cases when you deploy it out at the edge that, yes, people might shut down that machine in the factory when the shift goes home. It's normal, you save on power. Well, there's some PCs sitting inside the machine, they get powered off, right? But there's other cases when it might just go out unplanned as well. You don't actually know. And sitting in front of customers when the infrastructure guy says, we don't want to spend the extra $100 on the UPS so that you can do a graceful shutdown, that you have a minute of runtime to shut down your database, and the apps guy is sitting across the table saying, what? we don't know whether the database will survive. It might lose state, right? Because they have never run it in that environment. So sure, it's a container that's been running, it works fine, right? But they haven't worked under these assumptions. So these are things that you have to be aware of. You have to understand what are the constraints out at that edge when you want to move software there. So this poor DevOps developer struggles with this for weeks, months, whatever, figures out, can I test my database? Can I figure out that this stuff still works if the network is a bit intermittent, right? And now we're done, right? Well, no, then security person shows up and says, well, depending upon how helpful they are, they might come with something vague like this, like, you know, what attack surfaces do you have out there when you're putting this stuff out in some remote location with less physical security, et cetera, right? Or have you done some threat model and threat analysis of this stuff? And frankly, if someone had come to me early in my career and asked these questions, I would have gone, what? What are you talking about? Like, I write software here, right? I don't know what this is about. Today, hopefully people are more aware of, you know, security. But still, what does this concretely mean, right? So more useful questions is, okay, you're taking our intellectual property, our key AI models, algorithms, software that we've written, and you're putting that out at some location that might not have any physical security. It might have very limited, if no, sort of external network security, right? When it's running in the cloud, there's various firewalls and intrusion detection systems and whatever run by the cloud provider that you don't even see, plus your own level of security. And likewise, it's not only about the deployer sort of intellectual property, it's also about the data this stuff gathers for their customer out at the site. What is that customer data that you might store some of it on the disk, right? What are the concerns about that, securing that? And then in reality, you will have CVs, you will have vulnerabilities in software, whether it's these containers that the people developed, right? Whether it's in the operating system they use, whether it's in the container runtime that they're using, there's going to be some of these things. How do you actually get patches to those things out there? And in the data center, it's easy because you can just redeploy that VM running new versions, right? The VM that's running all of the containers. And in some cases, that could be semi-automated. Out here at the edge, well, at best, that's disruptive, but you don't necessarily have the same access. Can you actually get access to the system to go and do this? What tools are you using? How do you make sure that if you have 1,000 of them, that all 1,000 of them actually correctly update as opposed to get hosed in some state? So there's doing this stuff remotely at scale is actually quite of a challenge. And then, you know, how do you monitor for security things? People might have various, you know, sidecars, containers, whatever that can do monitoring. Do the same things actually work at the edge, or do you need additional things? If people are going to log into these systems, how does it integrate with the role-based access control and single sign-on that this enterprise is using? Whether it's the enterprise that built the machine or the enterprise that's deploying the machine, it depends on the sort of use cases. But these are very valid security questions to come and ask. So how do you actually solve this stuff? Well, one way of doing it is, since people have already figured out what Linux distro, what runtimes am I using, is that they figure out how to improve it, right? So do it yourself. So you can figure out how to harden all software. And there's plenty of help out there. I found a document that says how to harden Ubuntu Linux. It has scripts in it. That's why it's a bit long. It's 940 pages, right? You might be able to get suppliers today that have actually already done this stuff for you, that have actually followed these guidelines, right? There's another one for Kubernetes runtime. It's actually issued by some part of the US government. It's only in 60-odd pages, right? I don't think it has scripts, but it says this is what you need to go do. In addition, do you need to harden your containers, the actual applications you have developed, because they're going to potentially be more exposed to network threats out there. Not clear, right? And does it make sense for you to actually deploy inside your your OS out there, your Linux, some host-based firewall that you can remotely control, so you can actually constrain what the application traffic, what ports are open from the application. So you can actually make a bit of a sandbox for the application. So there's things you need to do if you want to do this yourself. But there's some harder problems. So these devices can be stolen, their disk drives can be stolen. How do you deal with this stuff? Well, people will say, but wait, we built all of the security technology. It's running on my phone, it's running on my laptop, right? Secure boot, full disk encryption. Great technologies. Doesn't fit, right? The secure boot that runs on a laptop, or to some extent on a smartphone, they're assuming that you can get out updates quickly enough, because the assumption is that, and you have some physical control of the hardware, because the assumption is that whatever supplier that signed this, they're signing it for all future. In theory, you can say this old version that's 2 years old is no longer allowed. No one has figured out how to do that at scale. There's mechanisms in your BIOS, in a PC, where you can say these hashes, these signatures are bad because someone found a serious bug in that thing 2 years ago. But that is not deployable as far as I can tell, right? So an attacker just needs to steal the device, go and put an old version with a known CV in it back in their shop, and then secure boot will say this is fine, right? And then they can figure out how do they attack it, given that that software has that CV. The CV could be in the OS, in the runtime, even in the BIOS, right? It can be different things they can try. The other tool we have, again, running on this laptop, right, is full disk encryption. Works great. Each time I power it on, I type a password or use a fingerprint or whatever, right? There's no user out there to do that. Where do you store the key? Technology is great, but you have no place to store the key other than on the disk, which is the one that gets stolen. So this is hard, right? So that's the hardest problem, right? Dealing with this stuff will get stolen. Do we know that it will get stolen? Well, in some cases, if you're deploying 10,000 of these ones, hardware out at various sites, you don't know, did something get misplaced, lost? Is it on the shelf somewhere? You know, the numbers say you're not going to know where all 10,000 of those are. So was it actually stolen, right? Can you tell? So it's going to be very challenging at scale. So yes, there's more basic stuff like how do I get updates out to this edge, right? It's still hard because of the network and physical access constraints. Doing immutable OS images makes this easier, because you now can at least more reason about these 1,000 or 10,000 devices, how many different versions of OS plus runtime plus containers do I need to worry about CVEs in? But it seems like it's useful to have some form of special purpose OS for this. Built using Linux, but not necessarily working the same way to address these things. And this is actually what we did. Started a couple of years ago based on, in LF Edge, Project Eve. And quickly, the slide is a bit busy, but I will run around. We have Eve here, right? Did the sound disappear? Running on the hardware. We have an API that's controlling this thing, and then at this end we have a controller. And there's actually a demo tomorrow that shows some of this stuff, but there's an LF Edge sandbox here that is one of the controllers that's free to use. There's also open source controllers part of the project. But the idea is to separate that stuff and have the controller help with some of these hard things, right? If you drill down a bit, there's a rather old slide, as you can tell from the style, but it's basically two partitions, booting, AB partitions, sort of things that many people have done to build more of appliance-like systems with an API, and then it can actually deploy things. It can run legacy like Windows 10, VMs. It can run different Kubernetes and Docker runtimes, etc. So that's sort of the big picture of this. But in terms of going back to, well, what does this help with? Well, it uses immutable read-only images. So you know that if you apply an update, you're applying a whole image. So you know that even if the power goes out while you apply it, it either got all applied and you switched over to the new version, or none of it, and you're still running the old. And A/B booting so that you can actually recover from this stuff coupled with that. Hardware and software watchdogs, so that if something goes wrong, you don't have to have a guy get in a truck or on an airplane to just go press the reset button, right? Doing this out at a solar farm or a wind farm, it takes days or hours to get there just to press the reset button, right? Just to power cycle the box. You don't want to do that. And unlike the data center, you don't have like a Pixie boot, remote power management, whatever type thing. These things are not, people don't pay money for that type of infrastructure around these things. It's just one server sitting out at the side. And the other part that helps with the robustness is to have an API, just like what people are doing with containers in Kubernetes, a declarative eventual consistency-based API. The thing that is unique here in EVOS is that we said, and that should apply to network configuration as well. We don't have time to go into details, but when like your static IP changes or your proxy settings change, how can you roll that out and do the same sort of A/B testing and fallback to do this robustly? So that's robustness. Now let's talk about security. Disable all physical ports like USB, etc., so that people can't plug in a USB stick and cause some harm. The applications can use those things, but the applications are separate from the actual EVOS. No users log into these things, because that API is key. It's being able to use the API as access, moving the users and the RBAC into the controller, so you have auditing and you have full control of things over there. Being able to onboard things. So some of this stuff will actually show up on the demo that they're running in the LFEdge booth tomorrow, but basically setting up mutual trust. And then a distributed firewall, so you can have a sandbox for this app saying, this app should only be able to send MQTT port number to AWS or Amazon, to AWS or Azure or whatever, right? Whichever ones the customer picks, the user picks. And you can deploy additional security appliances. So that's great, right? But I said the hard part was stealing the disk, right? This doesn't deal with stealing the disk or stealing the device. So here's where we actually had to do something that I haven't seen done before. These are all standard components, but no one has actually tried to solve this problem under these constraints before. So there's trusted platform module chips or firmware is actually quite standard on servers. The trusted computing group has specified these flows called measured boot and remote attestation. They are used in some cases, but not broadly used. There's a standard technique for sealing keys under TPM PCR measurements, right? And those are good building blocks, but actually putting together a solution, this is a bit more, it's more complicated than assembling your IKEA furniture, put it that way, right? And we actually did this stuff as part of the EVE open source project, so that you can avoid attestation if there are no changes. Because remember that the network connectivity might be down, so you want to be able to have the applications come up and run, and you can do that as long as there are no changes to the hardware, no one plugged in some other boot drive, right? No one changed the BIOS or the BIOS settings. The software didn't actually change anywhere. It can still come up and it says it's exactly what I was running before, right? All of the boot stack has not changed. And if there is a change, this remote attestation now means that it needs to go talk to the controller and say, here is my measurements, are these okay? I'm running this BIOS version, this version of EVOS, and somebody actually needs to pre-approve or post-approve saying, okay, this is okay because we know that we sent the guy out to update the BIOS on this device yesterday, right? And now you can actually say, it's still autonomous. It can run independently without internet connectivity, and it has this mechanism of updating things. And if you steal the device driver, if you steal the disk, right, or the device, if you steal the disk, you can't do anything because the keys are tied to the TPM chip. You steal the whole server with the TPM chip, you can boot what's on it, but if you try to change anything, in terms of its boot drives or BIOS or whatever, it will not be able to unseal that key for that disk. So you have to be able to find a bug that's in that version of the software that is currently running, right? You can't go back to an older version of, that was signed by someone 2 or 3 years ago and find bugs in that. No, you have to be able to find bugs in this. And when there's, CVEs that need to be applied, fixes for CVEs, I should say, that need to be applied quickly, well, the fact that it's always talking back to the controller when it has internet connectivity means you can actually drive out updates to this stuff at scale as well. So this is an example of building something using standard Linux pieces, but sort of with this special purpose in mind of dealing with these unique edge challenges. So feel free to join us, whether you're a user or the developer. Right? There is the open source project Eve. There's also this LFEdge sandbox where you can go try this stuff out. Maxi talked about it this morning at the keynote. And there's a demo tomorrow, I believe it's from 11 till 12, in the LFEdge booth that shows this in combinations with 2 other open source projects, Open Horizon and FDO. And if you need sort of motivation for coming and joining us, we built this stuff starting like 6 years ago or something like that. There's sort of evolution, but a lot of this is looking at what does it mean to run at this distributed edge? What are the challenges, and what sort of standard, open source Linux tools can we bring to this? Whether it's about being able to do snapshots, for not necessarily from a database perspective as a backup, but as a way of dealing with applications that somehow don't work correctly. So the application somehow messed things up and go back to the old version of the application, the container, and the data it was running on when it worked well last week. Right? And connectivity, CAN bus for vehicles, sort of usual things. Handling broken TPM chips, we rely a lot on those things. So the project is actually running into some of these things at scale where things don't seem to work the way they're supposed to, whether the chips are bad or the firmware is bad. And we're also working on sort of clustered compute and storage, so you can run 2, 3, 5 node Kubernetes clusters out at the edge. So you can now actually, if you care about having even higher availability and more flexibility in terms of doing rolling updates down the road, having a cluster of low-cost devices out at a given site, a retail location, a factory floor, or whatever, makes some sense. So that's work that's underway. We're also pulling in the real-time Linux patches and figuring out how far can we drive this stuff, when do we need additional hardware support for doing what level of real time. So those are some of the features that are underway. So questions. So ideally, you should know it ahead of time. There's some things that are hard to predict, particularly the closer you get to the BIOS. But even if, when a manufacturer publishes a new BIOS version, right, do they tell you this is actually the SHA-256 hashes of this BIOS as it boots, which might be different than the image you download, right? It's actually the way the TPM measures it as part of loading that piece of firmware into executed. So they don't today, right? So for EVOS, we know what sort of, this is what the kernel should measure as, this is what the root file system should measure at. So we're building things where you can, if you can predict it, you can put it in there. The way people do this that are security conscious, or very security conscious, is that they have one of each in their lab, in a secure lab. And then they say, okay, we know that this is exactly the same hardware, right? The same size SSD from the same SSD manufacturer, et cetera. So it will have the same measurements as these 100,000 out in the field, and run it there and run the new version there. And once you know that, now you have the measurements, and you can say, okay, these measurements are now acceptable for all of those things out in the field. You can update things remotely if you can. If you need to do something that's tied in with hardware, like I need to go add another disk drive, right? Yeah, the case is when you will send out a technician to do this stuff, but at least you have tried it so you know what to expect when the measurements come back. And the other thing is, if there is something that you didn't get it right, what we're securing here is the sort of user's and customers, applications and data, not the OS. So the OS will still boot. It will call home, and it will say, I have a problem, I can't unlock my disk. And it will say, this is what I measured, right? And then you can look at it and say, well, I don't know where that's coming from. I've never seen those measurements before. Is someone, tinkering around with this stuff? Is it a security attack? Did someone, just plug in a USB stick and the BIOS thinks that should change things, right? So at least you get some feedback, right? You know that it's not the power supply that died, right? So operationally you can tell the difference. But yeah, so there's processes, and the hope is that as industry evolves, that people will get better at this in terms of publishing things ahead of time, so you can actually predict things. So yeah, I mean, I think that there's sort of this evolution that, earlier people would deploy VMs, today they're deploying containers, tomorrow they would deploy models, right? So your sort of runtime will be different because the runtime will be the inference engine that's sitting out there. But sort of similar workflows. And there's some things we don't know, honestly, but the sort of notion that I want to run the same model across my whole fleet, right? So that means I should effectively be able to measure the model, right? So I should be able to say, okay, did someone else actually go modify this model, or is it actually the one I tested in the lab, right? And which versions of those do I have? So I think that's something that we can sort of reuse the same techniques doing that. In terms of the developer side of things, I mean, I think that it speeds up things, right? And then how do you actually test and code review and whatever? The things that were written with the help of Copilot type things, yeah, that still requires human beings as far as I can tell. Sort of like, do you know what type of mistakes to look for? Some AI will get better at that over time, and some other AI will code review what the first AI actually wrote, but it's probably, so there can be ways to accelerate the stuff in general. But. Sure, let's see. I don't have the announcement in front of me, but if you take this picture and remove all of the words, but you basically have a notion that there is a controller here, and we have 1,000 devices deployed at different places running Eve there, right? One of the challenges is that you want to do two things. You want to say, I want to have this controller specify the policies, whether it's about these PCR measurements, right? What versions are allowed, right? Which versions have been approved of operating systems, runtimes, containers, models, right? For my enterprise. So that sort of approval and policy thing being enforced centrally, but then you might not have bidirectional network connectivity to some places, right? These are typically referred to as air-gapped, right? It's actually, typically there actually are, even in very secure environments, they're typically one way, meaning that people can actually import things into those things, right? I think that in most sort of secure environments, people are running Linux. Well, they didn't write Linux from scratch. It's actually the same Linux, right? But they audit it as they bring it in. They take source code binaries, whatever, audit those things, and I would say, this is actually approved, we can now bring it in, nothing will ever leave, right? Hotel California, you can't check out, right? And so we're building things that are the same way, that you say, this thing might have some images to go deploy, containers, etc., and it has some configuration for these devices. And as long as you're allowed to bring those things in, now you can actually do centralized policy enforcement. These things are signed and encrypted, so, or they're signed at least, but you can actually audit them saying, hey, this configuration actually makes sense, I will import this stuff. Instead of it being done in a second, it might take a month. That's fine, right? It's all about eventual consistency. You will get that new configuration and the images that go with it. And now you can actually operate in this air-gapped environment where you're not letting any bit of information escape that environment, right? So that's the sort of building on top of this to say, we have a way of combining that plus what is actually known as local, what we're calling local control. This notion that you have policies, but you have someone that's operationally responsible. Should they be able to try to restart the application out in the field? Should they be able to restart the whole OS, right? What if something goes wrong? Can they revert back to the previous version of the application data that worked last week? In many cases, yes, but that's an operational issue, not a declarative, here's your intended configuration, right? You can think of it as, I'm not changing the software on my laptop, I just, pull the power plug, right? It's a way of trying to make it recover operationally that may or may not work, and the same thing applies in these environments where you want to have local operators that can operate but not change the configuration, and sort of global policy control. So all of these things fit together based on what we're seeing as these sort of constraints in deploying things out at the distributed edge. So that's sort of the lay of the land. But I think, to me, the key learning from this has been understanding these constraints out at whether things are on trucks, on factories, on solar farms, right? And sort of learning this stuff from people that have deployed and are working on deploying things. Because it's the same IT technology, we just use it slightly differently to sort of hit these use cases and workflows, right? So, okay. I think we're even over time, but thank you for the questions. Thank you very much.